All right, let's get going. I'm gonna try to get through a lot of material very quickly. Uh, for people who don't know me already, my name is James Prestwich. I am a protocol designer and kind of cross-chain engineer. I've been working in the cross-chain space for almost 5 years now. So I started off working on atomic cross-chain transactions with Bitcoin and Ethereum. Uh, and I've done a bunch of things with TBTC, with cross-chain bridges. And what I want to talk today is, why are the bridges burning? When we talk about cross-chain bridges, we've seen a bunch of hacks, we've seen a bunch of lost money. What is going on that is making these bridges fall apart? In order to do that, I'm going to have to talk a little bit about what is a bridge, how do they work, what's the mechanism underlying them, and why do the layers fail? So throughout the talk, I'm going to be using standard flowchart terminology. The rounded rectangles are start and end states. The little boxes are steps. The diamonds are decisions. The parallelograms are input and output to the process. Any diamond that only has one whisker out, assume that the other whisker means that everything falls apart and the bridge breaks and we don't go across chains today. So bridging blockchains. What is a bridge? The problem here is that you have Bitcoin and you want to use it in dApps, or you have Ether and you want to take it to Solana. We need to make something that goes in the middle that takes information from one chain, brings it to another chain. In order to do that, we want to lock up our ETH on one chain, we want to mint WETH on the other chain, and we want to use it in dApps over on Solana or BSC or whatever. And then we want to be able to get it back. We want to be able to burn that WETH, the representation on the remote chain, and get our ETH back on Ethereum. So this is, what makes it a bridge is the application, is the minting and burning, the supply management, saying that at any given time, we haven't increased the amount of ETH in circulation, even across multiple chains. We ensure that the mint corresponds to the lock and the unlock corresponds to the burn. And in order to do that, we need to cross this boundary between chains. We need to get info from one chain to another. And to do that, we use one-way communication channels. So we would have a communication channel from Ethereum to Celo and a communication channel from Celo back to Ethereum. And that's the only way to do this. Bridges are what we call dual simplex, which means they simulate two-way communication using two one-way independent channels. It is actually impossible to build a duplex channel in a blockchain for reasons we'll talk about in a second. So we have this intuitive understanding of bridges. We want to preserve supply integrity across multiple chains. We need to send information about the supply of Ether from one chain to another, and then send it, information about the supply of Ether on that chain back when we want to unlock our Ether. In order to do that, we need a cross-chain communication mechanism. And there are tons and tons of choices for these. And everybody just uses trusted multisigs. We have like 5 different options available, and everybody just loves multisigs. So we can dig into this a little more, obviously. We have one-way communications. We want to just send information from one dApp on one chain to another dApp on the other. Unfortunately, we have these barriers between chains. We can't just send info from one chain to another. This just doesn't work. You can't have the message received automatically. So what we need to do is we need to introduce a few more steps. We need to have the receiving chain process a transaction that came from the sending chain. When we're sending info from one chain to another, the only way to get info into the receiving chain is to make a transaction. So we have to have the sending chain dispatch a transaction. Unfortunately, we can't do that either because blockchains aren't users and they don't have private keys. So a blockchain can't sign a transaction for another blockchain, so you can't send a transaction from one blockchain to another. So we need to introduce, a bit more complexity. Uh, the thing we actually do in practice is we have the sending chain commit the message. So it commits to the burnt ether or the locked ether. Some off-chain actor, some person running a server somewhere, sees that message, decides to forward it to the other chain, and signs and dispatches a transaction. So some off-chain trusted third party has to sign and dispatch transactions in any cross-chain system. It is not possible to have a chain just dispatch a transaction to another chain. You need to introduce reliance on an off-chain, semi-trusted party. Because chains are passive. They can't reach outside themselves and affect the world. They can only update their own state. Communication, on the other hand, has to be active. We need to send this message, and we need to be sure that it's going to get there. And so in order to resolve that problem, we need to introduce communication channels and off-chain actors. That's how we cross the trust boundaries between chains. So let's get to the kind of fun part of the talk where I'm going to be spending a lot more of my time. Layers. How do bridges break? Why are the bridges burning? You may have seen this life cycle about 30 seconds ago in another slide. We need to go through 7 concrete steps in order to get a message from one chain to another. A lot of these steps are not very reliable or are difficult to engineer. So you probably have heard of Thorchain. A few months ago, Thorchain lost $8 million, which, I mean, in the blockchain space is not that much money, I guess. Thorchain lost $8 million when somebody broke their bridge. And in order to explain why, I gotta walk you through a little bit of Ethereum transaction processing. How does an Ethereum transaction hit a smart contract, cause other calls, and get processed? So how did Thorchain break? It broke in the commit and off-chain actor recognition of a message. And we're gonna talk about why. Ethereum processes a transaction starting from a user who calls a smart contract with some money and some data, and that smart contract might call another smart contract with money and data, and another and another. And you can go in, you can fire off events, which externalizes information so that off-chain actors can see it. And when smart contract 3 is done, it returns data to smart contract 2, which returns data to smart contract 1, which returns data back to the user. So you actually get really deep call stacks in any complex Solidity application. Instead of 1 to 3 smart contracts, we're probably interacting with 6, 10, 15 smart contracts on any relatively complex transaction. And what this means is that it's very difficult to write code that correctly observes, unwinds, and parses an Ethereum transaction to figure out what actually happened. Once you've gone through call stacks 10 deep, it's difficult to just know as a human and to know as a developer how to process what happened. So Thorchain wrote a huge Ethereum transaction parsing library in Go. And it's part of their node software. And it is what all of the multi-sig signers run when they're moving all of the money in Thorchain around. And what it does is it looks at an Ethereum transaction, and it looks for an event fired by the Thorchain cross-chain contract. It looks for an event that says how much ether was sent. How much ether is supposed to go over the bridge. It processes that event, it issues that ether over on Thorchain, and does whatever it's supposed to do. So the way Thorchain broke is that a user inserted a malicious contract into the stack. The malicious contract kept all of the ether, did not forward any value to the Thorchain smart contract system, and sent the ether back to the user at the end of the transaction. But due to a bug in their transaction processing system, instead of reading 0 value in the event from the smart contract, The Thorchain system, Thorchain chain, read the value that was initially sent in the transaction. So they read tx.value instead of the transaction receipt's logged out value. And it's really interesting because if you read their code, the buggy code, they actually read the correct value. They read the 0 value first, and then they later go back and overwrite it with the incorrect high value. And this allowed a user to fool the bridge into thinking that Ether had been sent, when in fact the user got to keep all of their Ether. And so this user issued themselves $8 million worth of Ether on the Thorchain chain and swapped it into something else and took it all back and walked away with a few $1,000,000. It is very difficult to spot these transaction processing bugs because, again, the call stacks in these are incredibly complex and nobody's very good at this. So Thorchain broke in the part of the stack that commits the message and has an off-chain actor see the commitment. They committed the correct message, and then the off-chain actor read an incorrect message. So the part of the stack that broke for Thorchain is, this big orange bubble right here. Everything else worked perfectly. And the moral of the story is that chain VMs are hard and taste bad. If you are writing custom Ethereum transaction parsing and tracing logic, you are doing something very wrong. You are doing something bad, and you should stop doing that. Chain-specific handling is error-prone, it's complex, it's arcane. This issue was like 1,000 lines deep into a .go file where no one has ever looked except the developers. We should not be writing chain-specific parsing. If we are relying on Ethereum to do our work for us, we should rely on the event or the state and nothing else. Never do transaction tracing. And if you are designing a cross-chain system, do not design it in a way that relies on transaction tracing or call stack management or anything like that. It's very bad and you're going to ruin it. Okay. Chain-specific logic should be on-chain. Chain-specific logic shouldn't be in the off-chain actor because you're going to wreck it. You're going to mess it up. It's bad. Okay. So the other one that I want to talk about that is also really interesting is Poly Network. Not Poly Market, that's a completely different product. Poly Network lost $600 million of user funds. And for me at the time, I was like, how is there even a bridge that I have never heard of that has $600 million in it? It was shocking. So this happened again a few months ago, earlier this year. The funds were eventually returned by the attacker, sort of, after someone threatened to dox them, and there was a whole lot of really interesting drama. It's a great story. You should go look it up. But I want to talk about the technicals. Is how did Poly Network break? They broke in a completely different part of the cross-chain stack. They actually broke in the transaction handling on Ethereum. So again, in Ethereum, we're going to use the call stack. And we're going to talk about how Poly Network specifically routes incoming cross-chain messages. So when the Poly Network cross-chain contract receives an incoming message, it's got the recipient contract, the data, the value, etc. And what the Poly Network system is supposed to do is take that incoming relayed cross-chain message and forward it with the data and the value to the recipient. This is some user-specified smart contract. So for example, an incoming Poly Network message might be instructions to call Compound with a specific blob of data and a specific amount of Ether. And so the off-chain actor takes that message, gives it to the system contract. The system contract unpacks it and sends it on to Compound. So the way Poly Network broke is that the user didn't specify Compound, they specified the Poly Network bank. And the way Poly Network is set up is that the treasury, where all of the cross-chain funds are held, is owned by the system contract, of course. It's the system, it owns the treasury. So the user had the system unpack this cross-chain message, send it to the Poly Network bank. The Poly Network bank sees that it's being called by the system and assumes that the system has admin privileges. And so all the user had to do was politely ask for all of the money. Just send a cross-chain message saying, please give me all of the money. And the Poly network system obligingly forwarded that message to the bank. The bank says, oh, the system wants all of the money. I'll just go ahead and forward all the money. So this is why cross-chain communication needs strict layers. It's why we make this separation between the communication channel and the handling. The layer violation here is that the bank is owned by the system, and the user can give the system arbitrary instructions coming in over the cross-chain communication channel. There's no distinction between local transaction processing and remote transaction processing. And in order to add that distinction, we need to make strict layers. We tend to use the concept of a router. There's a cross-chain channel that's like an Ethernet cable, you plug it into your router, and those are extremely separate things. So Poly network, because they had this confusion between local messages, like the Poly system moving around funds locally, and remote messages, user-defined calls that are coming in from a remote chain, coming in over the wire, any user could take all of the money at any time. And it just, took a few months and $600 million for someone to notice this. So we want these layers. We have cross-chain communication channels. We have cross-chain applications. They need to be strictly separate. App logic needs to be separate from channel logic. This has some side benefits. For example, if app logic and channel logic are separate, it means you can swap out the channels at any time. Or you can update the app logic without updating the cross-chain communication logic. Poly network was not able to do that, and although they did get, I think, most of the funds back eventually, it took a lot of time, a lot of off-chain action, and action from the trusted Poly network operators. It is it is unreasonable to have this kind of layer violation in 2021 when we have known how to write networking stacks for 30 years or more. I guess networking stacks 40 or 50 years, huh? So this is normally the time in my presentation when I would break for questions. It feels like this is going to be really difficult to do in this environment. So I'm gonna wrap up here, and I will be around the conference if you have any questions. If you have two takeaways from this talk, it's that you should never write chain-specific processing. You should never try to parse an Ethereum call stack. You should never do transaction tracing. If your bridge relies on that, it's gonna fall over and burn. And if you are writing an application, you need to make a strict separation between application logic and infrastructure logic. And confusing those will allow users to have, privilege escalation. These are classic errors from 30 years ago that we have reintroduced in a new context because we just didn't learn the history. So thanks for the time. I'm going to wrap up, and feel free to find me around the conference and ask any questions.